This is section 2.4, Solving Systems Using Matrix Inverses, part 2. Okay, we'll begin where we left off last time with this exercise. We're asked to find the solution to the following system by writing it as a matrix equation and using the inverse matrix. Okay, so well, first, let's write it as a matrix equation. So to get a matrix equation, what we want to do is we want to get the coefficient matrix and multiply it by the variable vector, set that equal to the constant vector, like this. Let's see, 1, 1, 7, 0, 1, 6, negative 1, 1, 6. That's my coefficient matrix. My variables are x, y, and z. And this should be set equal to the vector containing 4, 4, and 12. Okay, so I want to solve this. I could think of this as my coefficient matrix is matrix A. I could think of this column vector as X, and I could call this B. So what we want to perform is to solve for X, the unknowns. We want to perform A inverse times B. And in order to do so, we need A inverse. Okay. So to compute A inverse, we need to augment the coefficient matrix with the identity matrix and then do Gaussian elimination on it until we have the identity on the left-hand side, and then we'll have the inverse on the right-hand side. So what do I mean? I mean this. We're going to take this coefficient matrix, 1, 1, 7, and augment with a 3 by 3 identity matrix. Oh. Whoops, that should be a 7. Okay, so the second row is 0, 1, 6. 0, 1, 0. Third row is going to be negative 1, 1, 6. And the third row over here is 0, 0, 1. Okay, my first row op will be I want to add row 1 to row 3. Because I want to clear out this negative 1 right there. Let's see, so the first two rows stay the same. We have 1, 1, 7, 1, 0, 0, and then we have 0, 1, 6, 0, 1, 0. And then when we add the first and third rows, though, and store the result in the third row, we get 0, 2, 13, and then we have 1, 0, 1. Notice the first column is finished. We have 1, 0, 0 in that column, so I move on to the middle column, and I'm going to use that 1 on the diagonal to clear out the 2 below. So what am I going to do? I'm going to do negative 2 times row 2, and then add that into row 3. Okay, let's see here. I'll continue down here. I'm going to have negative 2 times row 2. That will be 0, negative 2, negative 12, 0, negative 2, 0. I'm going to be adding this row to row 3. Okay, so the top two rows will stay the same. 1, 1, 7, 1, 0, 0, 0, 1, 6, 0, 1, 0. But the third row will become 0, 0, and negative 12 and 13 is 1. 0 and 1 is 1. Negative 2 and 0 is negative 2, 0, and 1 is 1. Okay. So now this matrix is in row echelon form, but we can't stop here. We need to go all the way to reduced row echelon form to get the inverse matrix. So now we need to clear out elements above the diagonal, working from the rightmost column of the coefficient matrix to starting with the rightmost column of the coefficient matrix and then moving to the second column, the middle column. Okay, so let's see here. First thing I'm going to do is clear out the 6 above the 1. So I'll use this pivot here in row 3, and I'm going to multiply that by -6. So I'm going to do -6 times row 3 and add that into row 2. Okay. -6 times row 3. I'll write it below the matrix this time. That's going to be 0, 0, -6, -6, positive 12, -6. And I'm going to add that to, oops, not to row 3. I'm going to be adding that to row 2. I need to make this a little bit bigger. So I'm going to be adding it to this row. Okay. And what do we end up with? We end up with 1, 1, 7, 1, 0, 0. And then the middle row will become 0, 1, 0. Let's see, -6 and 0 is -6. 12 and 1 is 13. -6 and 0 is -6. And the bottom row stays the same. 0, 0, 1, 1, -2, 1. All right. Okay, so I'm not quite done with that third column of the coefficient matrix. I need to clear out the 7. So to do that, I'm going to do -7 times row 3 and add that to row 1. Okay, -7 times row 3, that's going to be 0, 0, -7, -7, positive 14, -7. I'm going to add that row to row 1. Okay. Let me come down over here and continue. And what are we going to get? We're going to get 1, 1, 0, -6, because -7 and 1 is -6, 14, -7. Okay, other two rows will stay the same. 0, 1, 0, -6, 13, -6, and we have 0, 0, 1, 1, -2, 1. All right, almost done. We have one more row operation to do. We need to clear out this 1 above the diagonal in row 1. To do that, I will multiply row 2 by -1. I'll do negative row 2 added into row 1. So what is the negative of row 2? I'll write it below the matrix. It'll be 0, -1, 0, positive 6, -13, positive 6. Okay, and I'm going to be adding that to, let me get rid of that circle. Oops. Adding it to this row. Okay, and the result all right over here. We're going to get 1, 0, 0. And then we're going to get 6 and negative 6 is 0. 14 plus negative 13 is 1. Negative 7 plus 6 is negative 1. Second row stays the same. 0, 1, 0. Negative 6, 13, negative 6. Last row stays the same. 0, 0, 1. 1, negative 2, 1. Okay. I'm going to zoom back out a little bit. All right. So now what have we done? We've transformed our matrix, our coefficient matrix A, that had been augmented with the identity matrix via a finite sequence of elementary row operations into an augmented matrix of this form, where we have I on the left and this will be A inverse on the right. Okay, so now we have A inverse. We can actually compute, we can actually solve the linear system. I'll finish the problem right here down below. So let's see, what we want to compute is, I'll write it in here, x, y, z, our column of unknowns, is going to equal A inverse, which is this 0, 1, negative 1, negative 6, 13, negative 6, 1, negative 2, 1, times the column vector of constants, or the B column vector, which had 4, 4, and 12 in it. So 4, 4, 12. Excellent. So this is our x is equal to A inverse times B. In other words, what we've done here by computing the inverse matrix, we've transformed this problem of solving a linear system into matrix multiplication. I just need to multiply A inverse times B now. Of course, this is a 3 by 3. This is a 3 by 1 matrix, so the resulting matrix will be 3 by 1. And how do I get that? I'm going to do the dot product of each row of A inverse with the column vector B. Let's see, I'm going to do this partly in my head here. Let's see, 0 times 4 is 4. 1 times 4, or sorry, 0 times 4 is 0. 1 times 4 is 4. Negative 1 times 12 is negative 12. 4 and negative 12 is negative 8. Okay. The next dot product is going to give me negative 6 times 4. You know what? I'm going to write this one out. I'll write it out right over here. Negative 6 times 4 plus 13 times 4 minus 6 times 4. These are both going to be negative 24. And then the product in the middle, 13 times 4, that's 40, plus 3 times 4, which is 12, that's 52. Okay, negative 24, negative 24. That is negative 48. And negative 48 plus 52 is, what is that? That's going to be positive 4. Okay. Final dot product, we need to do 1 times 4 plus negative 2 times 4 plus 1 times 12. So we get 4 minus 8. That's minus 4. Minus 4 plus 12 is 8. Okay, and there we go. We get the solution negative 8, 4, 8. So x equals negative 8, y equals 4, and z equals 8. Okay. Now we could certainly test this by plugging our values back into the original system, and that's usually a good idea. But to check this work, I'm going to switch over to the calculator here, and I've already put this coefficient matrix A and the constant column vector B into the calculator's memory. I'll show you. Here's A. Yeah, that matches the coefficient matrix. Yep. And then I've put our constant vector into matrix B. Yep, that has 4, 4, and 12 in it. And I am going to compute, using the calculator, I'm just going to compute A inverse times B. How do I do that? Well, this it couldn't be easier. You recall the matrix name, A, and then I want to compute the inverse of it, so I just press the x to the negative 1 key, and I get A inverse. It'll compute it for me. And I want to multiply that by B, so I recall B from the matrix menu, and there we go. A inverse times B. Oops. Well, let's see. I have a mistake in my solution, apparently. Let's check that out. Negative 6 times 4. That's negative 24. 13 times 4, that is positive 52. Oh, and negative 6 not times 4, but times 12. Okay, so this part of my calculation was wrong. It was negative 6 times 12, which is negative 72. Okay, yeah, that's totally different. Let's see, so that would be 24 plus 72. That is 6. That's 96. And then we do 96 minus 52, and we get 44. Yeah, so our answer will be negative 44. Okay. Oops. Well, good thing I checked. Okay, so now the answer is correct. And notice how easy it is to do this on the calculator. So yeah, the calculator is really a great tool for solving linear systems. Okay, let's move on to this next exercise. Let's see here. I'm going to switch back to full screen here. The manufacturer of portable tools has 3 sets: Basic, Homeowner, and Pro, which must be painted, assembled, and packaged for shipping. The following table gives the number of hours required for each operation for each set. Okay, yeah, we've got Basic, Homeowner, and Pro tool sets. And okay, yeah, so for the basic set requires 1.4 hours of painting per set, 0.6 hours of assembly, and 0.9 hours of packaging. Okay. and then so on and so forth for the other two kinds of sets. All right, let's continue on. If the manufacturer has 74.3 hours for painting per day, 46.3 hours for assembly per day, and 44.4 hours for packaging per day, how many of each type of set can be produced each day? Okay, so they give us a little hint here on what variables to use. They say here, let X equal the number of basic tool sets, Y will be the number of homeowner tool sets, and Z will be the number of pro tool sets. Okay. So the question there is that last sentence. How many of each type of set can be produced each day? So the manufacturer has some constraints here, which we need to satisfy. And we can solve these kind of constraint problems using linear algebra. So the basic idea here is going to be, well, if we multiply the numbers, notice, I'm just going to write on the table here, but if I multiply 1.4 times x, that's going to give me the number of hours I need to paint the basic tool sets. Okay? And then if I do this 1.7 times y, because this is going to be the x column, the y column, the z column, if 1.7 times y, that's going to give me the number of hours I need to paint all of the homeowner tool sets. And then 2.5 times z, that's going to give me the number of hours I need to paint z professional tool sets, right? Okay, and similarly for these other values, this second row, if I put plus signs in here, plus, 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 so this first equation is going to be the total painting hours. Okay. The second one is going to be the total assembly. I'll just kind of hours, shorten that. Can't write that small. And then if I do the same thing with this row, multiply 0.9 times x and add 0.7 times y, and then add 1.9 times z, I'm going to get the total number of packaging hours. I'll just use double tick marks there. For the total packaging hours I need to package all of the basic, homeowner, and pro tool sets that we make. Okay, but I only have these limited hours. I only have 74.3 hours for painting and so on and so forth. So this should be 74.3. And then the other one, we have 46.3 hours for assembly, so this should be 46.3. And the last one is 44.4 hours for packaging. Okay, and I want to write this linear system now as a matrix equation, and then use some technology to solve the system for me. I'll just use the calculator. Okay, so how do we set this up as a matrix equation? Well, I think we can take that grid of data as is and write 1.4, 1.7, 2.5, and then 0.6, 1.1, 1.6, 0.9, 0.7, 1.9, take this matrix and multiply it by x, y, and z. And that gives us all of the stuff on the left-hand side of the equal signs. And this should equal this column vector of values 74.3, 46.3, and 44.4. Okay. So that's the system we need to solve. Okay. Now I've already put these matrices into my calculator to save some time, and I called this matrix D. We'll call this one X, and I called this in my calculator, I used the E matrix for this column vector. So we have this linear system is represented by dx equals E. What do I want to solve for? The unknowns, the X matrix. How do I do that? Well, X is going to equal D inverse times E. Right? I just take that equation, dx equals E, and multiply on the left of both sides of that equation by D inverse, and I get X is equal to D inverse times E. So let's do this on the calculator. Let's see here. Okay, I put these matrices into the calculator like I said. Oops. Let me go to the matrix menu. D, notice D is a 3 by 3 matrix. Let's pull that up. Okay, yeah, you can check that that does match the data table we were given. And then E, the E matrix, yeah, it has 74.3, 46.3, and 44.4. This is correct. Okay, so then we just need to compute D inverse times E. So I'm going to recall the D matrix, raise it to the -1 power, multiply it by E. And there we go. Okay, and what do we get? We get 5, 19, and 14. Okay, so recall that this capital X represents this column vector containing lowercase variables x, y, and z. And x, y, and z represented the number of basic tool sets. Y is the number of homeowner tool sets, and Z is the number of pro tool sets. So the solution is this manufacturer has enough time to create 5 basic tool sets, 19 homeowner tool sets, and 14 pro tool sets. Okay, great. So the takeaway from this section is what? I think that the main takeaway should be that we can solve linear systems of equations by writing them as a matrix equation and then algebraically manipulating that matrix by multiplying both sides of that matrix equation by multiplying both sides of the equation by the inverse matrix. And ultimately, we're turning this difficult problem of solving a linear system into matrix multiplication. Of course, we need to compute the inverse matrix as well, but technology can handle that for us. So, all right, this is then concludes section 2.4, part 2.